0.7. But in a lot of applications, different level is expected rather than just 0.7. So in order to achieve a clipping level that is other than 0.7, what we used called as biased limiters. The only difference is you are going to see a DC source in series with the diode. What it doesn't change is, it doesn't change anything except when the diode is reverse bias, what do we say? The diode will act as, that means you can remove this whole branch even it has a power supply on it. That means that whole branch will be gone as long as the diode is reverse bias, which is same as before. Yeah. Yeah, as long as it's in series, whether you put before or after, even along that same branch. The only point where you even consider the DC voltage is when the diode is in the forward condition. So it's, even though it appears to be like this, but it's a lot easier to deal with since you're now aware of how the clippers work. So let's take few examples in testing the behavior of these clippers. If we needed a voltage other than 0.7 volts. So let's take this. But it's very hard to tell which side will be clipped and how much without doing some calculations, exact clipping levels. So the circuit will be identical as before. So let's put this diode like this and maybe add some DC voltage. Let's say this is a 1 volt. And let's see what happens to this specific circuit. Well, let's just so that's a 500 ohms as the load resistor on this side. So the first thing with these two, exactly the same process, whether we are talking about, okay, let's start with the same way and see how, at what instance it would be different. So let's say we are going to talk about positive cycle and then the negative cycle. Correct? That's always the first thing we say. Secondly, what we do? So you first figure out what polarities the diode is carrying. So this would be negative. But in addition to that, now you need to know the polarities of the power supply as well. So in here, which side of the power supply is positive? The top, since it's a longer, and negative. So that's one addition to whatever we do like before. So now we decide what biasing we're about to do. So what do you think? Positive cycle means? Look at the diode orientation. Positive cycle means, yeah, positive cycle is reverse bias. We agree, right? We don't even go there right now. Let's wait a minute and actually see what really happens. That automatically means negative cycle means forward, right? So in reverse bias, what we do? Reverse bias means the diode acts as an open circuit, meaning that diode will be gone along with the DC power supply as well, meaning that the circuit pretty much looks like same as before. If you take away that whole branch, The circuit is as simple as a series circuit, correct? So if you take away diode, even though you have a power supply, that current will not go anywhere because that branch is in open. So we can completely remove that branch and perform our voltage divider principle, which would be what? So 500 over 1500 or 1.5K times your 5 volts. Yeah, so positive cycle is like, this is positive, that's negative, but the diode is negative there, positive here. Yep. 1.67, something like that. So that's 1.67 towards the positive cycle. So are we clear? Reverse bias is always easy. As I mentioned, it's voltage divider always, since that branch will always going to be get removed. 6.7. Yes, that's the voltage divider. So when we're dealing with forward bias, this is where it's slightly different. Forward bias means the diode will begin conducting. So the diode will have 0.7. This is how I would like to draw only that branch. Since it is 0.7, but the negative on the diode is on the top, positive is on the bottom, correct? So the diode will have the 0.7. There is a supply too right below it with the given polarities like that. So that's negative, that's positive, and that's negative. So let me erase this. So that would be 0.7 right here. Correct? So that branch becomes like this, right? So what do you think the voltage level here would be? The total voltage level. We know the DC source value. So as if these two sources are connected in series, correct? So what do you think the resultant total voltage would be? So let's say one answer is 1.7 when you add them, right? Okay, we have another result which says negative 1.7. So what else?
So is it not positive 1 volt into the negative 0.3?
So that would be what?
Or 0.7 would be positive 0.3, right?
So that's another result. So which one we're gonna? So the easiest way to dealing with this, you see that these two batteries, where they're connected positive to the positive, right? One of the easiest way to tell is the top one is negative 0.7, correct? The reason I picked negative is because I start with negative. The next one is positive 1 because the first plate of that supply is positive. So what would be the result? Positive 0.3, and this is very important value. The signal will not even go to negative and it will be clipped at positive 0.3 volts. So the reference may be somewhere here. The signal will not even go to the negative side of the time axis because the clipping voltage came out to be at positive 0.3.
So negative cycles will always have negative 0.7.
Depends on what? The diode. Whatever the voltage you are looking here is depending upon what happened to this branch. Because now the diode becomes active, so that negative 0.7 on the top, positive 1 on the bottom. That would be because you place them in series, so they are additive, so that's positive 0.3. So the signal only starts at positive 0.3 and going all the way to 1.67. If you flip it. Yeah. And most of the circuits won't work. For example, if you take any circuits, they won't operate on a negative voltage. But internally they do. But you don't just see it. Like if you just consider like TV remotes, if you flip it, they won't work, right? The circuit designed like that. But internal to the circuitry, there are circuits that only works on the negative voltage. But we just visually don't see it. So you will see in transistors, when we discuss transistors, that's where some things you will see as negative voltages. They run with negative voltages. But you see the difference, or there is no difference when we're dealing with reverse bias. But what you will see is, as long as the diode is forward bias, you need to carefully consider the orientation of the diode and the orientation of the power source to be able to determine what would be the effective voltage. So just for the sake of discussion, so we good on this, on how we got that 0.3? So just for the sake of discussion, like you mentioned, what happens if I flip this DC source over? I'm going to leave that 1 volt right here, but I'm going to simply flip this around. Is there any effect on, let's consider this as like a new problem if you want to redraw it. Right. Is there any impact on the positive cycle? Because the diode still be reverse bias, so it won't affect that 1.67, correct? So it's still going to be 1.67. But what do you think will happen for the negative cycle? That is where when the diode is forward bias, what do you think the level of voltage would be? So you said negative 1 point. So this is one result. I've said, okay, it goes to negative 1.7.
So the other one, positive number, negative this one.
So are you going to get negative 1.7? Because now the diode was still at negative 0.7, correct? The reason I picked negative is since the negative is on the top. But for the source, since the negative is on the top for the source as well, it would be negative 1. So negative 0.7, negative 1. So that is going to be negative 1.7, meaning that the signal previously, it was at 0.3, but now this will go all the way to negative, what is it, 1.7 is it? So it will go all the way to negative 1.7. So the clipping level would be negative 1.7 volts.
So with
Depends on, that is correct. So as long as forward bias, you can have either positive 0.7 or negative 0.7 based on the orientation of the diode. On the diode we're talking about this. His question was only on the diode, not like when you add it. Your question was on the diode, isn't it? It's just the diode, not like including this one. It's just this guy right here. Because if I flip the diode around, then you would see positive 0.7, right? But it would be on that side. Yeah. Yeah. Again, we didn't, in this example, we didn't change the diode orientation. So it's only the battery orientation. But even if you flip the diode, it's the same process all the way through. So these are what usually called as biased clippers. Since biasing means DC voltage, so that's why the name biased clippers or biased limiters. But it's a very similar, except you need to be careful about the polarity of the DC source. With the diode. Because if you take away, that's correct. If you take away the DC source, what clipping level it would be? Negative 0.7, correct? If you take away the DC source, then it would be just negative 0.7. So if you keep the DC source, then depends on the direction of DC source, you either add or subtract. What?
It's tricky when you start moving that DC source around.
It's easier if you see it this way. Because the DC voltage is not going to change, correct? So that means in this situation, the anode of the diode is being held at that negative 1 volt. So the anode of the diode is always held at negative 1 volt since it's not going to change. But cathode of the diode is usually sees that AC signal coming in, which is usually changing in voltage. So these are basically what clippers or limiters are. There may be one slight variation that you might see in all these possible limiters is without the load. For example, if I don't have a load and let's say the circuit was simply just like that, and let's say he just say that, okay, this is where my output voltage is. So what I'm going to expect right there? So am I going to expect exactly the same thing? What do you think? So it's not load on this side, correct? So what will change from this analysis? So does the forward and reverse bias changes? Like let's consider just this circuit for the sake of discussion. The positive cycle still reverse bias is correct. Reverse bias means you already don't have this resistor, correct? Right? And you don't have that whole branch because reverse bias takes away that whole branch. So the circuit pretty much is like this, isn't it? So if I measure right here, what I'm going to read? I'm going to read a source voltage. Voltage across an open circuit is the source voltage, meaning that there is no need for this voltage divider, because as long as that whole thing is open, the voltage on an open circuit is a source voltage. So the only difference is the positive cycle is all the way through 5 volts. There is no limiting right there. The positive cycle is all the way through 5 volts, because that whole circuit becomes open, because you don't have a resistor that closes it to even do a voltage divider. But on the other side, what do you think? It would be the same. On the other side, would be no effect, because you are still in parallel to, because once the diode is active, you're still collecting across the parallel. It's not open anymore. Correct? So other side will not create any impact. But whenever you see that whole circuit becomes open, then it would be the source voltage, whatever the source voltage is. Whether it is positive cycle, then it would be 5 volts. Or if not, that would be negative 5 volts.
That 1K resistor doesn't do anything.
Because of an open circuit, there would be no current flowing through the 1K. So the voltage on 1K is 0. So Ohm's law, right? I times R, when I is 0, it doesn't matter what R is.
But in the other direction, it would still be negative 1.7.
That is correct. In the other direction, this branch is still intact, correct? Because of the diode. The diode is conducting. So that branch is still intact. So on the other side, you still get negative 1.7. So that's pretty much what clippers are.